Thanks for the introduction, Mehmet. And thanks very much for coming today. My name is Quan, and I'm on the 2024 job market this year. So I'm very glad to be here to present one of my recent work, which is about personalized delivery and fulfillment optimizations. So this is a joint work with Mehmet from McGill and with Senthal from CU Boulder. So to begin with, let me briefly describe my research interests. And my current focus is on complex e-commerce related operations. And I have 3 projects under this scope. The first project studies order fulfillment in the context of middle mile delivery. And this paper is under the second round review at Operations Research. And the second project is the focus of today's talk. I will share more details later. And this paper is under the first round review at Operations Research. So the third paper, we try to understand the impact of shipping charges on the customer purchase behavior, as well as the revenue for online retailers. So this paper is under development. Besides that, I'm also interested in optimizing platform services. And one project I'm working on is about a matching problem with two-sided arrival, and they are non-stationary, or they are non-stationary. And this project is motivated by the new feature from Uber called trip radar. So if you are interested in any project, please let me know. I'm glad to chat offline. So let's go back to today's talk. As you may know, online shoppers have different preferences for shipping methods. Like someone prefer faster fulfillment and they are willing to pay for it, but others are more cost sensitive. So they are willing to wait in order to get a free shipping. And in cope with that, online retailers start to offer multiple fulfillment options to online shoppers and let them to choose the most preferred ones. For example, Instacart allows customers to choose from different delivery dates. And Amazon offers different fulfillment options, and each specify a delivery date as well as a shipping cost. So you may wonder why retailers want to complicate their operations by giving multiple choices instead of just giving a cheap and fast fulfillment option to every customer. So the answer is the operations is never free for those online retailers. We have to think about their profit margins as well as try to satisfy customer as more as possible. So here we need some sort of management to help them improve the improve the fulfillment operations. And well, our collaborator also face this challenge, and which largely motivates this research. So this is a company that operates in Eastern Canada who is specialized in online grocery retailing. So this company works with more than 800 local farmers, and they serve customers from more than 400 different cities across Canada. And they are expanding, by the way. So in terms of the fulfillment operations, this retailer have 4 different ways. First, they can do home delivery with either a local logistic provider or an international one. And the difference is the available fulfillment capacity, as well as the unit fulfillment cost. And the retailer can also send orders to pickup locations with the local logistic provider. And later, customer will come to those places and pick up the orders themselves. And this the pickup point can be, for example, the local convenience store or restaurant who agree to participate or who agree to collaborate with this online retailer. And lastly, customer can choose to go to the warehouse and pick up the orders directly. So in that case, no logistic resource was consumed. As you can see here, we need to manage different logistic resource, and we need to decide which logistic provider we use and how many orders we fulfill with it, right? So this is the web page you will see if you shop from this company. As you can see, there are a lot of things happening here. So your decision may be affected by the type of service, for example, the shipping speed, how much you are going to buy from us, and of course, how much you are going to pay for the shipping service. Then we can simplify this problem by focus on the trade-off between the shipping speed as well as the shipping cost, and try to include the rest factors into how we determine this cost value. So as you can see here, we have to manage we are facing a demand management problem because we need to control the number of customers who submitted their orders with a specific fulfillment option. So our collaborator faces both demand management as well as capacity management. So the natural question we try to ask is, how can they improve their profitability by jointly optimizing both aspects, right? In addition to that, we also want to know the extent to which this joint optimization will benefit this online retailer. So to answer those questions, we first developed a joint stochastic dynamic programs that incorporates a general discrete choice model. So any choice model works for us. And then we proposed a tractable heuristic policy to solve the problem, which has the provable performance. So regarding the benefits, we see first, both demand management and capacity management are important. However, their importance depends on the customer preferences. Be more specific. If the customer is speed-driven, they want to get their orders as fast as possible, then demand management is more important. But if the customer is cost-driven, then capacity management can significantly improve the performance. Okay, so our paper is closely related to three different literatures: the order fulfillment literature, the choice-based revenue management literature, as well as the network revenue management with flexible products. But due to the time constraint, please allow me to just skip this slide. Okay, so let me try to describe what we're going to model as a sequence of events before we head into the technical part. As you can see, customer arrive, first lands on the web page and start to browsing and do their shopping. They can see whatever they want and add whatever product they want to buy into their cart. So after deciding what to buy, they will go to this checkout page where they will be given a list of fulfillment options. And two things may happen from there. First, if the customer is satisfied with one option, they will submit their orders. In that case, the purchase is completed and the retailer can get the money and they have to keep track of these orders. However, on the other side, if the customer finds no option satisfactory, and they will just simply leave without complete the purchase. So in that case, we call the cart is abandoned, and then nothing happens after that. So the retailer needs only to fulfill those submitted orders periodically from the warehouses. And due to the potential logistic capacity constraints, we have to categorize orders into urgent orders and less urgent orders so that we can try to prioritize urgent orders, and those less urgent orders can wait in the system. Well, this type of urgency is specified by the fulfillment option. For example, if I choose one-day delivery or same-day delivery, then my order is more urgent. If I choose standard shipping, that takes maybe 5 to 7 days, so my order is less urgent. Okay, so lastly, the retailer will rely on different logistic provider to execute the fulfillment operations on their behalf. And each provider will offer a flat rate for each order they ship and commit some sort of capacities for every period we do the fulfillment. So we're going to model each and every subsequent events in the following way. We start from the fulfillment option. It conveys two pieces of information. First, a guaranteed latest arrival time, K. We call it fulfillment window. You can think maybe I need to wait 1 day or 2 days or 3 days to get my order. That's the fulfillment window. And the second information is how much I pay for this service. That's called shipping surcharge. As an example, we have 3 options here. That's from Amazon. So if, let's say, Amazon is going to make a fulfillment decision every week, every day. So we can encode the options in the following way. The first one will be 1 and 199, because as you see, we have to fulfill these orders by the end of the day. And I can charge you 199 pounds. And similarly, I can either fulfill by today or tomorrow in the second option. So K equals to 2, but I don't charge you. Similarly, the third option is 3 and 0. And more generally, we assume to have at most K different fulfillment windows, and we can select those fulfillment charges from a discrete set called R, like 99 cents, 199, 279, etc. So this model well captured the trade-off between the fulfillment, between the shipping speed as well as the shipping costs. And it also works well for the case of Amazon and our partner. So talking about the customer behavior, we actually use a general discrete choice model to describe that. As you see here, pi sub of KR means the probability we're going to choose this option out of a given list. For example, we have 3 options here. So you may choose the first one or the second one with a probability of 40%, but you're not going to choose the third one because it's dominated by the second one. However, you may still leave without purchase at a probability of 20%. This can happen if I want to get my orders today, but I don't want to pay for this, right? So as I mentioned earlier, different orders have different fulfillment window, and we may not be able to fulfill them to fulfill all of them right away. So we need a way to keep track of those unfulfilled orders, right? Let me use this location as an example how we do that. So by the time we need to make a fulfillment decisions, there's a list of unfulfilled orders from this location, which we group them to different groups based on the remaining fulfillment window. Like this is the amount we need to fulfill by the end of the day. This is the amount we need to fulfill by tomorrow, and etc. Like K days later. So after the decision has been made, some of those orders are fulfilled right away, but some will stay in the system to the next period, like tomorrow. But their remaining fulfillment window will decrease by 1. Okay, and during the next period, new orders arise based on the customer preference and what fulfillment options we display to them. So you see, we endogenize the demand realization here. And all of these piles can accumulate in a similar way. So this process just goes on to the end of the horizon. We are dealing with a finite horizon problem. For those orders that runs out of fulfillment window, they will leave the system with a penalty. So you can think in the following way: we are going to hire some special fulfillment service, which is very fast but very expensive. So their cost will be this penalty cost for us, okay? And the last assumption we made in this project is try to capture this dependency of multiple logistic providers in fulfillment operations. Let's say we're going to hire UPS, FedEx, and DHL for the operations. And well, each will give us some capacity, like I'm going to ship 200 packages for you, 300 and 400 packages for you. And we charge some flat rate cost, like $5 per order, $10 per order, and $15 per order. So as the retailer, I'm going to use the most cost-effective provider first. That means I'm going to use UPS first, followed by FedEx, and then DHL, right? So this results in a convex relationship between the total fulfillment quantities to the total fulfillment cost. So we generalize that concept, says, okay, a fulfillment cost function will be convex and increasing. So this is trying to capture, we have infinitely many logistic providers we can use. Okay. Okay. So the objective in this project is try to maximize the expected revenue by deciding 2 things. First, which fulfillment options we show to each customer, and second, how to fulfill those orders at the end of each fulfillment cycle. So we can formulate the problem as a stochastic dynamic program, And there are two parts involved. The revenue is very closely related to demand management, and the cost part is closely related to capacity management. As you can see, this suffers from the curse of dimensionality as stochasticity and high dimensional problem. So there's no hope we solve it optimally, and we shift our lens to develop heuristic policy and hope it have good performance. So our solution to this problem is this two-phase policy. And from the high-level perspective, we try to get some reference policy for assortment decisions as well as the fulfillment decisions in some tractable way in this offline phase. Then we are going to deal with the demand management as well as the capacity management separately in the online phase. Specifically, we're going to tailor this reference policy of assortment decisions as well as the fulfillment decisions based on what's the focal customer and based on what's the current system state. And of course, we hope our policy will have some good performance. That means it will not deviate too much from the optimal policy. So let me maybe spend like 5 minutes to briefly introduce how it works. So in this offline phase, we use the choice-based deterministic relaxation to turn the original problem into a convex optimization so that we hope we can use a commercial solver to solve it. However, the convex optimization is not solvable. It's intractable because the number of decision variables grows exponentially in the number of available fulfillment options. So to deal with that, we rely on the following structure properties. What we observed is I'm going to show you some assortment with a positive probability. Then this assortment must be some special kind. It's called efficient assortment, by the way. So our strategy is, can we identify each and every this type of special assortment and hope that the total amount does not grow exponentially. Therefore, we can solve the DET just using this subset of assortments. Luckily, yes, we do have those. Although we do not have the theoretical complexity on the number of elements here, but empirically, it's a very small set.
Efficient means optimal, right?
Efficient means optimal in the sense the revenue you can get versus the resource you consume is the best way. Yes, that's right. Okay, so once we have this reference policy, we can go to the online phase. And we are going to deal with demand management as well as the capacity management separately. In terms of the demand management, we do two things. When there's a new customer, we're going to select one assortment S with the probability gamma. But we're not going to show S directly to you. We're going to scan each and every option and remove those non-viable. So non-viable means if, as a customer, I'm choosing this option, then the marginal revenue it generates is strictly smaller than the fulfillment cost. That means this order, if you choose this option, generates a negative profit. In that way, of course, I don't want to show it to you. So I removed it, I hide it from you. So in the capacity management, we also do two things. First, we scale the referenced fulfillment policy based on the actual realized demand. That handles the feasibility concerns. And then we have to limit the total fulfillment quantity from each warehouse by some threshold. And the second move is closely related to another structural property we discovered. It says, if I'm going to use some warehouse to fulfill those orders, and the total optimal fulfillment quantity should be bounded such that this criteria must be satisfied. As you can see, that means the marginal fulfillment cost should not exceed this penalty cost. Somehow intuitively makes sense. So we actually use this criterion to check if we are going to use some warehouse to fulfill those orders. And this will implicitly give us the threshold value.
And these are like these are optimal for the whole process, but they are based on the parameter.
Absolutely. The optimal threshold is state dependent, but we somehow to find a way to proxy it. Okay. So of course, I'm hiding a lot of technical details here, but if you are interested, I'm happy to talk about that one. So to check the performance of the proposed heuristic, we introduced two benchmark policies based on whether or not we're going to optimize capacity or the demand management. So this is our proposed heuristic. We optimize both, but the benchmark policies only just optimize one dimension. And we're going to use the percentage profit loss as the measure. So we create two sets of simulations. First, we choose the fulfillment cycle to be 1 week. This is based on the actual operations. And then we identify three fulfillment options from the data. And we can calibrate a multinomial logic choice model to describe the customer behavior. In terms of the fulfillment network, this retailer only operates one warehouse. And we choose 21 cities in the Greater Montreal area. And we estimate the customer arrival rate based on the real data. And in terms of the fulfillment cost, it's a two-segment piecewise linear cost convex function, which describes the fact this retailer used two logistic providers. Okay. So what we see from the data is most customers prefer faster fulfillment. That's expected. So in this scenario, if we optimize capacity, we see a 33% profit loss. But if we optimize demand management, we see only 3.8% loss. Okay? And if we optimize both, we can improve the performance to 2.8%. However, it's not too far away from this one, right? So the message here is when the customer prefers faster fulfillment, demand management is more critical. This is because most customers will want to get their orders as fast as it possible. So in that sense, we do not have much room to optimize our fulfillment. We don't have the room to balance the demand from time to time. Okay. But yes,
the lower the number is, it's better, right?
The lower number, the better.
Why?
Because that's the loss. That's the how much you are away from the optimal.
But you said optimal is too difficult to.
Yeah. So I'm using good point. This is the upper bound for the loss. So you know the actual performance is smaller than that.
So this is the worst case.
This is the worst case bound. Yeah, right. Absolutely. Thanks for the clarification. So this is not the whole story. So we then massage the customer preference to generate another set of simulations. In this way, in this case, customer prefers slow but cost-effective fulfillment options. So as you can see, demand management is also important, but you see a 22% profit loss. However, if you optimize both, you see huge improvement here. The gap is only 1.6%. So from the second set of simulations, we see that when the customer prefers cost-effective fulfillment option, although demand management is important, but capacity management can significantly improve the performance here. Okay.
And the capacity management, you mean that there should be like a lot of restriction on the capacity, right? That's why there is gain because you are managing
the capacity. I mean, I can have like maybe 5 trucks every day for shipment, or if I need to ship additional orders, I need to buy some ad hoc resource from other places, which will be much higher, right? So we want to balance the demand from time to time in order to utilize in the best way of those cheaper resources we have. So in the second set of simulations, we really try to capture the key trade-offs in reality. I hope you still remember, this is the checkout page. And we try to capture 4 different things. So first, we identify 3 different types of customers. They will buy different amounts from us. And then we identify 4 fulfillment options based on 2 dimensions, the type of service and the speed. So with all this, we can then determine the fulfillment cost. For example, if you buy a lot, we'll give you complimentary free shipping, but you just buy a little and you want home delivery, you have to pay for it. So then we can calibrate a customer type-based multinomial logic choice model, and this is way complicated than the first scenario. So it says medium and high value customer prefer home delivery, as expected, and low value customer have a more diverged preference. So we implement, again, 3 policies in this complex scenario. We see, okay, demand management is important, but joint optimization can even close the gap here. So the message to our collaborator is here, demand management is more important than the capacity management, given their customer does not change their preferences. Okay. So to wrap up, we proposed a heuristic to solve the joint optimization problem, which is suitable for any discrete choice model. And in terms of the managerial insights, we see both demand and capacity management matters, but their importance depends on the customer preferences. So for future research, I have 3 things to talk about. First, in the case we don't know the customer preference, we have to learn it while we try to optimize the fulfillment operations. That's one thing. Or maybe you want to optimize your fulfillment operations with a non-flat rate cost structure. So think about this in the following way. Because we're going to send orders to pickup locations, and sometimes in a large batch. So we may be able to negotiate and utilize this scale, or the economy of scales. So to capture that, you need your cost structure to have a fixed part as well as a variable part. As you can imagine, the problem is no longer convex, which requires different sets of techniques to solve. And lastly, I think it's also interesting to think about the pricing problem when the retailer implements different shipping programs. For example, you can choose standard shipping, pay or not. You can choose the contingent free shipping, like if you buy a lot, we give you free shipping. Or if you are willing to pay a premium, like Amazon Prime, then you are entitled to free shipping. So in this case, the pricing problem may be really, really complicated and interesting. So that concludes my presentation. Thanks very much for listening. I'm happy to take any questions.